This is part 2 of the walkthrough of the AQA GCSE Chemistry 2023 Higher Tier Paper 2. Question 6. This question is about chromatography. A student investigated an orange food coloring using 2 different types of chromatography paper. The food coloring contained a mixture of red and yellow dyes, was soluble in water. This is the method used. Figure 3 shows how the student set up the apparatus. So we have a lid with our chromatography paper inside, our beaker, a start line drawn in ink, an orange food coloring on the start line, and we have some water towards the bottom of the beaker. 6.1. The student made 2 mistakes when separately setting up the apparatus. Give 2 mistakes the student made. Well, what are we expecting to happen in this experiment? We're expecting there to be separation of our orange food coloring because it should contain a mixture. Now, for that to happen, the water, which we call the mobile phase, will need to interact with the chromatography paper, which we call the stationary phase. The water would get drawn up the paper, and the orange food coloring would then separate based on the solubility in the water and the attraction of the chromatography paper. But the problem is that the start line in this case is drawn in ink. So when it interacts with the water, then the start line is going to move, and then that's going to make it difficult for us to be able to do any calculations, and it will make it harder for the orange food coloring to separate. So the first issue, or the first mistake, is the start line is drawn in ink. And we explained the reason why. The second mistake now is the water should be below the start line. Now, why is that important? Because the moment that the water interacts with the ink, it's going to dissolve. And this time, because the water level is above the start line, it's going to then wash and dissolve both the ink and the orange food coloring, so nothing would actually travel up the paper. So the problem is the water level is above the start line. Another student set up the apparatus correctly. Table 3 shows the results. So we have the 2 types of chromatography paper, the red and yellow dye, and we have a distance moved by the dye, a distance moved by the water, and the RF value. 6.2. Determine value X in table 3. Well, looking at type B, the yellow dye, we don't know the distance moved by the dye, but we know the distance moved by the water, and we know the RF value. So we have enough information to calculate our distance moved using the numbers that's underlined. So first thing that we want to do then is we want to calculate our RF value. We have that. So we want to use our equation to calculate RF value. So our equation is RF value equals distance traveled by the substance divided by distance traveled by the solvent. What we need to then do is just plug in the numbers that we are given. We're given the RF value, which is 0.60. We're given the distance moved by the water, and the water is a solvent in this case, so that's 12.0. So we just need to figure out then something divided by 12.0 will equal 0.6. Well, if we rearrange the equation, then it would just be 0.6 multiplied by 12. If we do that, we should get an answer of 7.2 centimeters. Changing the type of chromatography paper resulted in different RF values for the red dye. 6.3. Explain why the RF values for the red dye are different using the two types of chromatography paper. Use table 3. Well, we have two different types of chromatography paper. Let's go back to the table just to have a look at the results. What's going to be different about the chromatography paper then, as we were saying before, is to do with attraction to the dye. Now, how does it work? The stronger the attraction of the dye to the paper, the less distance traveled by that substance, in the case dye. The weaker the attraction, the further up the paper the dye will travel. Now, going back to the question again, why are the values different? Well, a reminder that the other factor that we have to take into account is how well the solubility is of the dye in the solvent. But remember, both types of paper are using water as the solvent, so you'd expect the solubility to be the same for both dyes. For each dye for the same dye in the different chromatography experiments. So, what's the issue here then? Well, looking at the RF values, we can see that the red dye has a smaller RF value compared to the yellow dye on both pieces of paper. So if the solvent is the same as we said, then it's got to be this attraction. So what we can say then, because the red dye has a lower RF value, that means that its attraction to the paper is stronger. So let's start to formulate our answer. We're going to use a table for 3. So the RF value for red dye is lower. What does this tell us then? It tells us there is a stronger attraction of the red dye to the paper. So what does this mean then, if there is this stronger attraction? Well, let's check our results one more time. The distance moved by the dye is lower. So what that means then is that the time in which it's spent on the paper distributed is going to be greater. 6.4. What other changes in the investigation could result in a different RF value for the red dye? Well, as we've been saying multiple times in this question, it's two factors: the attraction to the paper and the solubility in the solvent. In 6.3, the main reason why there was differences in the RF values is due to the attraction to the paper. The solvent was the same. So in this situation for 6.4, a different RF value could be the result of using a different solvent. Question 7. Manganese dioxide catalyzes the decomposition of hydrogen peroxide solution. Oxygen and water are produced. Explain how a manganese dioxide catalyst increases the rate of decomposition of hydrogen peroxide. Well, key words in this question: catalyst. We should have knowledge about a catalyst, what it does, how it works. So, what is the catalyst going to do? It says it's going to increase the rate, but how is it going to do that? What catalysts do is they lower the activation energy. So that means that less energy is required to get the reaction started and form our products. But this lower activation energy means that it's taking a different pathway than what it would normally do without the catalyst. And that's what we're doing by explaining. A student investigated the rate of reaction. This is the method used. 7.2. Explain why the mass of the conical flask and contents decreased. So, in the method, they're using a conical flask. They're putting the hydrogen peroxide there. They're adding some of the manganese dioxide. And this is being placed on a balance. And a timer has been started. The mass is decreasing. We need to explain why. Well, let's go back to the information at the beginning of the question. It's catalyzing decomposition of hydrogen peroxide. Oxygen and water are produced. We've underlined it already. So why would a mass decrease when oxygen and water are produced? Well, oxygen is a gas. Water can exist in gaseous form, but that would mean that it would be water vapor, and they haven't specified that. So the liquid form is what we have for this water here. Well, in the method, they haven't stated, like they did in the earlier part of this paper, that a stopper was used. So there is nothing to stop anything entering or exiting this conical flask. And if oxygen is a gas, gases like to move freely. So what's going to happen then is the oxygen is just going to escape from the conical flask, and that's what's going to cause the mass to decrease. So first thing that we need to just make sure that we know and state is oxygen is a gas, and therefore the gas will escape the conical flask. (7.3) Figure 4 shows the results for 50 centimeter cubed of 2 moles per decimeter cubed hydrogen peroxide solution and 1 gram of manganese dioxide. A tangent to the line has been drawn at 75 seconds. So our tangent is our straight line. We can see that it's touching at 75 seconds. Determine the rate of reaction when the time was 75 seconds. Give your answer to 2 significant figures. 4 marks. So, by them drawing a tangent on our line, what it is going to allow us to do is to calculate the gradient. Now, to find the gradient, it's going to be the change in 2 values on the y-axis over the change in 2 values on our x-axis. A reminder, though, that when you draw a tangent, it will assume that the gradient will be the same at any point on the line. So we can take any 2 points, and we should expect the gradient to be the same. So what we're going to do then is going to try and find our points. So we're going to start with the top part and the bottom part of our straight line. What we then need to do is just read along to the y-axis and the x-axis and be able to get our numbers. So let's take this first point towards our y-axis. We can see that the interval is going to be 0.4. So each line is 0.4. So our first value would be 1.24. Our second point on our y-axis, and we read it along, it's just one line below 1.80. So take 4 from that, and that'll be 1.76. Now we go down to the x-axis. Our first point, you can see that it's on that solid line there, and that should be 25. And we do the same thing for our second point, still on the solid line, and this time it is 125. So what we're doing now is we're going to find the change in these two values. So 1.76 minus 1.25, that's going to be 0.52. And 125 minus 25 is 100. So there's our change in y, 0.52. Our change in x is 100. So we just need to divide that, and it will be 0.0052. And that is already into significant figures. The results for 50 centimeter cubed of 2.0 moles per decimeter cubed hydrogen peroxide solution and 1 gram of manganese dioxide are shown again on figure 5. The student repeated the investigation using 50 centimeter cubed of 1.0 mole per decimeter cubed hydrogen peroxide solution and 1 gram of manganese dioxide. Sketch the expected results of 1 mole per decimeter cubed hydrogen peroxide solution on figure 5. So let's compare these two experiments now. Experiment 1, they used 2 moles per decimeter cubed, 50 centimeter cubed of hydrogen peroxide and 1 gram of manganese dioxide. How is that different in the second experiment now? In the second experiment, they used 50 centimeter cubed, so that's the same. But they used 1 mole per decimeter cubed, whereas in the first experiment, they used 2. So you use half the concentration of hydrogen peroxide solution. But they use the same mass of manganese dioxide. So the only difference is that concentration. So how is that going to look on the graph now? Well, if you've got a lower concentration, that's going to cause a lower rate in the reaction. So how would you show a lower rate in a reaction? You would draw a less steep line. When we do our sketch now, we're expecting a less steep line. But we need to start at the same starting point as this already added line to our graph. So it needs to start from 0. So a less steep line would be to the right. But we need to finish it now. And if the concentration is halved, that should then mean that there are less reactants, and that should mean that we should have a lower mass lost. Remember, one more time, the concentration is halved, so we should expect then half the total mass lost at the end. So looking at our graph now, with the 2 mole per decimeter cubed, it finishes at 1.60 grams. So half of that then would be where our horizontal line would need to be, and half of 1.6 is 0.8. So we're going to go up and start to curve our line, but it needs to finish at 0.8. And that's where our 2 marks come from. 1 for going a less steep line, and 2 for leveling off at 0.8. Question 8. This question is about polymers. Chloroethene can be used to produce an addition polymer called polychloroethene. The displayed structural formula of chloroethene is shown. A.1. Draw a circle around the functional group on the displayed structural formula that allows chloroethene to produce an addition polymer. Well, we're looking for a unique group that is always involved in polymerization. Well, you're always going to be dealing with an alkene in this addition polymerization. So we need to remind ourselves of what's the functional group of an alkene. It's going to be the double bond, so we just need to circle there. (8.2) Complete the equation for the production of polychloroethene from chloroethene. So what's going to happen in this polymerization now? Well, we need to make a repeating unit of monomers. Our monomer is already here. But for that to happen now, we need more bonds that are available. And the only way we can get another bond that's available is to break this double bond to produce a carbon-carbon single bond. So that's what's going to need to happen first. We're not going to lose any of the other atoms that are present, so we need to show all of those intact like before. But what we need to do then is we need to show that we can add on some more molecules. So to do that, we add some more bonds on either side of our carbon atoms. But remember that poly means many, so there could be an endless amount of these monomers that we're getting. So to denote that, we put a small n outside of our bracket. 8.3. Polyethene can be strengthened with wood particles to make a building material. The building material consists of a wood particle reinforcement embedded in a polyethene matrix. What general name is given to materials like this? So we have polyethene which exists. That's one material. It's going to be added to wood particles to make another material. So essentially you have a material made up of 1 or 2 different materials. What is that known as? That's known as a composite. (8.4) The amino acid beta-alanine has the formula shown. Beta-alanine polymerizes to produce a polypeptide and a small molecule. Name the small molecule produced when beta-alanine polymerizes. So, it's reminding yourself of what happens during a polymerization reaction. Now, during a polymerization reaction, you are actually carrying out something called condensation. Now, think about the word condensation. Condensation is the process of turning a gas to a liquid. Now, when we think about condensation, are really thinking and focusing on one type of liquid molecule, and that is water. So when we're taking this beta alanine and that polymerizes, so bonds with another beta alanine molecule, what's going to be released is going to be a water molecule. So this will be the small molecule which is produced. Eight 8.5. An amino acid can be represented as shown. The relative formula mass of this amino acid is 75. Calculate the relative formula mass of the section of this amino acid molecule represented by the grey box. The relative atomic masses of hydrogen, carbon, nitrogen, and oxygen are shown. So, the total relative formula mass of this whole molecule is 75. We're shown some of the elements that's involved. So what we can do is we can find the relative formula mass of these groups, and then we can subtract the total value of these relative formula masses of these groups from our total, which is 75, and we should then get the answer for the amount for the grey box. So let's start with our NH2. So N is 14, H is 1, but there are 2 lots of it, so I need to multiply that by 2, and then we can just add that together. So 14 plus 2 is 16. So we know that this NH2 group is got a relative formula mass of 16. Let's do the same on the other side now. Carbon we know is 12. Oxygen we know on its own is 16, but there are 2 lots of them. So 16 times 2, that's 32. And then we know that hydrogen again is 1. So finding the total of that, 12 plus 32 plus 1. So you will get a value of 43. You'll get a value of 46. You'll get a value of 45. So what we need to do now is add the total, 45 plus 16, and that will give us 61. And then finally, we just need to subtract that from the total RFM for the whole amino acid. So that's 75 minus 61, and that will give us 14. So relative formula mass of the grey box is 14. Figure 6 represents part of a naturally occurring polymer molecule produced from glucose. Figure 6 shows part of the polymer. 8.6. Draw a circle around the repeating unit in the polymer in Figure 6. So we've been dealing with polymers in these questions previously. So a polymer is a repeating unit of monomers. So what we just need to do is identify a unit on its own that is repeating. Well, you can see that there are groups at the top that are repeating, groups at the bottom that are repeating. You can see that there is a bond that is joining things together. So what we can figure out then is that this structure is the monomer, seen as it is repeating more than once in our figure. 8.7 suggests the identity of this polymer. Now, the information at the top of the page says that this is a naturally occurring polymer which is made from glucose. So we've just got to remember now, what can glucose join up to make? Well, it can make up many things. What you will deal with in your organization knowledge in biology is starch. However, you may also know of cellulose, glycogen. So all of these are potential polymers of glucose. Figure 7 represents the structure of a naturally occurring polymer. 8.8. Give the general name for the 4 different monomers which make up the structure shown in Figure 7. So let's just name Figure 7. We know that it's DNA. What do we know about DNA? Well, it says it's a polymer, so that means that the monomers are something that we should know. Well, the monomer from DNA are called nucleotides. And as the question says, there are 4 different ones, and they vary based on the base. A, T, C, and G. Again, something that you will know from biology knowledge, paper 2, inheritance. So, our general name is nucleotide. So DNA is an example of a polynucleotide. 8.9. Name the shape of the structure shown in Figure 7. Well, as you can see, Figure 7 is twisted, but it looks like there are 2 twists. What you've heard about for DNA is its shape, which is very important and very iconic, the double helix.